Good evening everyone. Welcome to another lecture of engineering mechanics. This is lecture number 6 and in this lecture we are going to cover a very important topic known as free body diagrams. Why it is a very important topic? Because whenever you need to find forces, whenever you need to analyze forces, be it statics or kinetics, you have to first draw the free body diagram of a body. So what is a free body diagram and how do we draw this? That is what we are going to cover in today's lecture. But before we get into today's lecture, let's solve the assignment of the last class. This is our culture that we every day start the lecture by solving the last class assignment problem. So this was the question given to you in the last class. A system with three forces and a concentrated moment at A is shown in figure. The system is replaced by an equivalent force system with a single force and a single couple at point O. Magnitude of the equivalent couple at O is. So we have how many forces? Three forces. 100 Newton acting at 30 degree with horizontal, 200 Newton vertically downwards, 50 Newton vertically upwards. And we have a couple also, an anti-clockwise couple of 50 Newton meter, and now we need to find the equivalent couple at point O. Chalo. Now first we will find the components of this 100 Newton. We will resolve this 100 Newton force. So it will have two components. This will be 100 cos 30 and this will be 100 sin 30. Now we will calculate the net moment at point O, and while we calculate the moment, we will consider anti-clockwise moment positive and clockwise moment negative. Okay, it is up to you whatever sign convention you want to assume, because they are asking only the magnitude of the couple. Okay, so what will be the magnitude of couple at point O? 100 cos 30 is already passing through point O, so it will not create any moment. 100 sin 30 will create an anti-clockwise moment, so it will be 100 sin 30 multiplied by 4 meter. This 200 Newton will create a clockwise moment, so 200 into 2 and it will be negative. This 50 Newton is also passing through O, so it will also not create any moment, and this 50 Newton meter is an anti-clockwise moment, so it will be plus 50. So what is the net moment at point O? So 100 sin 30 means 50. 50 into 4 is 200. 200 minus 400 is minus 200, and minus 200 plus 50 is minus 150 Newton meter. Negative sign means the moment will be anti-clockwise. Clockwise. We have considered anti-clockwise moment to be positive and we are getting minus 150, means it is clockwise, right? But they are asking us only the magnitude of the moment, so it will be 150. So this is the answer. Very good, very good. Chalo. So let's move on to the lecture. So today we are going to see the concept of free body diagram, and it is the first step in solving any problem of statics or kinetics. Okay, only in kinematics we don't consider forces, we only consider the motion of the body, we study about the motion of the body. So that is why in kinematics we don't draw free body diagrams, but in statics and kinetics the first step in solving any problem will be to draw the free body diagram. Now first let's understand what do we mean by free body diagram. Okay, see, whenever you need to analyze the forces of a body, what you need to do, for example, let's say there is a building. There are lot of members in that building. All these members are connected to each other. I want to calculate the forces acting on one particular member. For example, let's say I want to calculate the forces acting on a beam, and this beam is connected to lot of other components. All these members are applying forces on each other. For example, the roof which is resting on top of the beam, that roof is applying a downward force on the beam. Now the column is supported on the beams, so column is also applying some force on the beam. The wall is also in contact with the beam. So all these members which are connected to the beam, they are applying forces on the beam. So if I want to calculate what are the forces acting on the beam, the first thing I will do is I will isolate this beam. Isolating means it is right now connected to all the other members, right? So I have to detach this beam from other members. Okay, and whenever I will isolate any member from beam, I will show the interaction between that member and the beam using forces. For example, the roof is applying a downward force, or the roof is resting on the beam. So if I isolate the roof from the beam, I will show whatever downward force the roof is applying on the beam. Then when I will isolate the columns from the beam, I will show some upward force acting on the beam. So in order to calculate the forces acting on the beam, I need to isolate all the other members and I need to show whatever forces they are applying on this beam. So this sketch of the beam that I will draw will be known as a free body diagram. So what is the definition of a free body diagram? Read this. Free body diagram is a sketch of the selected system consisting of a body, part of a body, or a collection of interconnected bodies completely isolated from other bodies, showing the interaction between them by forces. Let me break this statement, let me break this definition for you. Free body diagram is a sketch of selected system, means you can draw the free body diagram of any system you want. Okay, so you select the system. See, if I want to calculate forces acting only on the beam, then my system will consist of the beam. But let's say I want to calculate the forces acting on the beam and columns together. So I will not isolate the columns from the beam. I will draw the beam along with the columns. So now my system will be beam plus columns. So selected system means whatever you are studying, whatever bodies you are studying. So it can be a single body, it can be part of a body. In some cases, we also consider part of the body. Okay, so it can be a body or part of a body or collection of interconnected bodies. In this case, beams and columns are what? Interconnected. So if I select these, then it will be known as a free body diagram of interconnected bodies. Okay, completely isolated from other bodies. So if I am drawing the FBD of beam, I will isolate it from all the other bodies. I will disconnect it from all the other bodies, showing the interaction of all other bodies by forces. I hope this definition is very clear to you. Okay, so whenever we need to calculate forces, analyze forces acting on a body, we isolate that body from all the other bodies. But whenever we are isolating, we have to show the forces acting between these bodies. Okay, now let's consider an example. and I will take a very simple example. I will consider two boxes. Let's consider two boxes. Let's consider a blue box resting on a yellow box, and these boxes are resting on earth, a surface of the earth. Okay. Now, right now we have two bodies. We have a blue box and a yellow box. So we can either draw the FBD of both these boxes together, or we can draw the FBD of these boxes separately. It will depend upon the question. It will depend upon the question whether you need to only draw the FBD of blue box or yellow box, or you need to draw the FBD of blue and yellow box together. Let's say that weight of the blue box is W1, weight of the yellow box is W2. Okay. Now understand, in the first case, I will draw FBD of both these boxes together. Okay. I will draw the FBD of both these boxes together. So what I am doing is, I am isolating only the yellow box from this surface. I am isolating this yellow box from the surface. I am not isolating the blue box and yellow box. I am only isolating the yellow box from the surface. Okay. Now understand, whenever we draw the free body diagram of a body, the first force that you need to apply is the weight. Why? Because every body is interacting with earth. How it is interacting with earth? The earth is pulling this body downward, right? Every body which is near the surface of the earth is attracted towards earth. The earth is pulling that body towards it, and this force is known as the weight. So whenever you draw the free body diagram of a body, first thing you do is you apply the weight, because we usually forget about it. Believe me, in most of the cases, people usually forget about the weight. Okay, when a body is subjected lots of forces, okay, sometimes we forget about applying the force, weight. Now, in a lot of problems, the weight of the member is negligible, considered negligible. But here, let's consider the weight of the body. So, the first force that we will apply is weight of the body. The weight of this blue box and this yellow box. This is W1 and this is W2. Now, understand, we have isolated the yellow box from this surface. So I have to draw the interaction of yellow box and the white surface. How they are interacting with each other. How they are interacting with each other. This yellow box is resting on top of this surface. So it is trying to push this downwards, right? The yellow box is trying to push this white surface downwards. Let me call this N1. It's a normal force, so I will call it N1. Now this white box will apply an equal and opposite force on this yellow box. Why equal and opposite force? Remember Newton's third law. You might have studied Newton's third law in school, right? Every action has an equal and opposite reaction. So if the yellow box is applying a downward force N1 on the white surface, then the white surface will apply an equal and opposite force on the yellow box. So there will be an equal and opposite force N1 on the yellow box. So this is the free body diagram of both blue box and yellow box together. Right now I have only isolated the yellow box and the surface. I have not isolated the blue box and the yellow box. Okay. Now understand this. When these two are together, this N1 and this one N1 is cancelled. Can you see this diagram? When the yellow box and the surface are together, there is no force here. Why? Because both are applying equal and opposite force on each other. So it gets cancelled out. Okay. Now in the second case, what I am going to do is, I am going to isolate blue box as well as yellow box. This is my blue box. This is my yellow box. Now understand. First, draw the weights. W1, W2. Now, the yellow box and the blue box both are isolated from each other. So I have to show the interaction between these two. How these two are interacting with each other? The blue box is applying a downward force on the yellow box. Like this. Let me call it N2. In return, the yellow box is applying equal and opposite force on the blue box. So this will be N2. Now can you see this diagram? Here there is no force between them. Why? Because when they are together, these two forces are cancelled. When they are together, both are applying equal and opposite force on each other. So the forces are cancelled. But when they are separated, isolated, then I have to show the interaction between them. Now the yellow box is again isolated from the white surface. So I have to show that interaction force also. So this is the FBD of yellow box as well as blue box separately. So do you understand what do we mean by free body diagram? A free body diagram is a sketch of a body, part of a body, or interconnected bodies completely isolated from other bodies, showing the interaction between them with forces. So we have isolated them and we are showing the interaction using the forces. Now understand this thing. Usually in structures or machines, the members are connected to each other by means of some type of joint. Okay. The members are supported by means of some types of support. Whenever we isolate a body from its support, we need to know what type of force there will be between the support and the body. This force can also be called as a reaction. For example, here, when I isolated the yellow box from the earth, then whatever force I am getting, I can call this force as a reaction, because this yellow box was applying a force on this white surface. That was the action. In return, it got this force. So this is a reaction. So whenever we isolate a body from its support, we need to know what type of reaction it is going to get. Otherwise, how we are going to draw the free body diagram, right? There are different types of supports. Okay. So we can divide all types of supports in 3 categories. Whatever type of support there is, we can divide all these types of supports into 3 categories. One by one, we will see in which category what forces will be developed as a reaction force. Okay. So the first category of support is known as a roller support or a frictionless surface. A roller support or a frictionless surface. I will tell you about frictionless surface later. Right now, I will explain you about the roller support. Okay. There is a student in the live chat who is asking my name. Beta, if you see the first lecture, I have introduced myself, then you will get my full introduction. Okay. Just look at the first lecture, first few minutes of the first lecture. So let's say this is our body. I have not drawn the complete body. Okay. So let's consider this is our body and this is the support I am talking about. This is known as a roller support. What do we mean by a roller support? A roller support is a type of support that allows free translation parallel to the surface. Right now, this roller support is resting on this surface, right? So this body can freely move parallel to this surface. This roller support can also be on a vertical surface. Okay. It can also be on a vertical surface. So it will allow free translation parallel to the surface, means vertical direction the body will be free to move. Right now it is free to move in horizontal direction. Now understand, the roller support can be drawn like this or this. Okay. If I isolate the body from this roller support, what reaction force I am going to get? Understand. This body can freely move in X direction, right? So there will be no reaction force in X direction. The reaction force will be only developed when the body will not be able to move in X direction. But right now it is free to move. So there will be no force, but the body cannot move in Y direction. In Y direction, what is happening? In Y direction, this body is applying a downward force on this support because it is trying to move, right? Due to the weight of body, it is trying to move downward. But the support is not allowing the body to move downward. So the body is applying a downward force on the support. In return, the support will apply an upward force on the body, right? Understand this. If I am trying to move past this wall, let's say I am trying to move past this wall, what I will do? I will apply some force on the wall. In return, the wall will apply an opposite force on my hand. So that is what is happening here. When we are trying to move the body in X direction, there is no force. Nobody is stopping us. So there is no force. But when we are trying to move the body in Y direction, this support will stop us. So we are getting a force in Y direction. Okay. Is it clear? Now, if I try to rotate this body, will this support be able to restrict the motion? If I try to rotate the body, will this support be able to restrict that motion? No. So I will not get any couple as a reaction. When will you get a couple as a reaction? Right now I am only getting a force as a reaction. When you will get a couple as a reaction? You will get a couple as a reaction if you do not allow the body to rotate. Right now, the body can freely rotate. Can you see this pin here? So right now the body can freely rotate. So I will not get any couple as a reaction. Okay, so there is only one force, a single force acting perpendicular to this surface. This surface is horizontal. So I am getting a vertical reaction. Let's say my roller support is on an inclined surface like this. Let's say my roller support is on an inclined surface. Something like this. This is the body. So in this case, what is going to happen? We will get a reaction force like this. This reaction force will be normal to this surface. Okay. Right now the surface is horizontal, so I am getting a vertical reaction. If the surface is inclined, I will get an inclined reaction. So reaction force will be normal to the surface on which there is the roller support. Okay. Now let's understand about the frictionless surface. This is also another type of support which comes in the same category. In case of roller support, you are getting only one reaction perpendicular to the surface, right? In case of a frictionless surface also, you will get the same thing. So let's say that this body is resting on two surfaces, a vertical surface and a horizontal surface. These points are point A and point B. And let's say that these surfaces are frictionless. There is no friction. They are very smooth. So when I isolate the body from these two surfaces, the horizontal and vertical surfaces, I will get reaction. Understand? This body cannot move in this direction, right? It can freely move in this direction at this point, but it cannot move in this direction. So I will get a reaction from here in this direction. Similarly, at point B, it can freely move in this direction, X direction, but it cannot move in Y direction. So I will get a reaction in Y direction like this. So let me call this NA or RA or RB, or let's not call it anything. So you can see that both these type of supports are of same category. We get only one reaction force normal to the surface. Let's move on to the second type of support, which is known as a pin support or a hinge support and a friction surface. In the last case, there was a frictionless surface. Here, there is a friction surface. Okay. So this is the second category of the support, a pin support or a hinge support. What do we mean by hinge? It is nothing but a pin. You can see that there is a pin here. Now, if I support a body using a pin, then the body cannot move in X direction. It cannot move in Y direction. It can rotate about the pin, but it cannot translate in X or in Y. So here what is going to happen is, there will be one force in X and one force in Y. Now understand, you might be thinking, sir, how do you know that this force will be towards right side? It can also be towards left side, na? Even this force can be downward. It is not necessary it should always be upward. So how do you know the direction of these reactions? We don't know the direction of these reactions. Understand this. I only know that there will be a force in vertical direction, but whether it is upward or downward, that I don't know. I only know that there must be a reaction in horizontal direction, but whether it will be towards right or towards left, I don't know that. So whenever you are deciding the direction of a reaction, you assume any one direction, plus x or minus x, plus y or minus y. If you solve the problem and you get a positive answer, means your assumption is correct. And if you solve a problem and you get a negative answer, means your assumption is wrong. So mathematically, at the end, we will get to know what is the right direction. Okay. So you don't need to worry about the plus or minus x on plus or minus y. You should only know whether it should be in x or y. But plus x minus x, you don't need to worry. Assume any one direction. Solve the problem. If you get a positive answer, your assumption is correct. If you get a negative answer, your assumption is wrong. I hope it is clear to you. Now understand this. Whenever we get a hinge support, we get two forces. But in some cases, in order to reduce the number of forces, we consider the resultant of these two forces. Right now I have a reaction in x and a reaction in y, but in some cases we replace these two forces with the resultant of both these forces. Why do we do this? In order to reduce the number of forces. When will you do this? That you will get to know when we will solve problems. Okay, I will tell you in which cases we will consider the forces in x and y separately, and in which case we will consider the resultant of the forces. Okay, so you should know the concept, but when will you use this concept, that you will get to know when we will solve the problems. So I hope the hinge support or the pin support is clear. Now let's move on to the friction surface. This is also the support of same category. So let's say this time we have friction forces acting at point A and point B. Now the friction force is a force which acts parallel to the surface. So at point A, we will have a normal reaction and a friction force. Similarly at point B, we will have a normal reaction and a friction force. So here we are getting two forces, right? We are getting two forces just like the hinge support. So this is also a support of the same category, second category. Now let's move on to the third category. Now this is fixed support. It is also called as built-in support. Now what do we mean by fixed support? Fixed support means we have completely restricted the motion of the body. Now it cannot translate in x, it cannot translate in y, it can also not rotate. So now we will have a reaction in x, a reaction in y, and we will also have a couple. This time we will also have a couple. Now understand why we are getting a couple. We are getting a couple because this support will restrict the rotation of the body. The body will not be able to rotate about this point, right? So we are getting a couple. In other cases, the rotation was not restricted. So that's why we were not having any couple in this case or in this case. But in this case, the rotation is completely restricted. So we are also getting a couple. So these are the three categories of supports. Now, does this mean that there are only three types of supports in this world? No. There can be multiple types of supports in this world. But whenever we draw the free body diagram of a body, we will assume all those supports to be of any one of these three categories. So how we will decide whether the support is category number 1 or category number 2 or category number 3? For example, let's say a body is welded to another body. Let's say that this is a beam it is welded to a surface. So if it is welded to a surface, it cannot translate in X, it cannot rotate in Y, and translate in Y, and it can also not rotate, right? So it is behaving like a fixed support, right? So I will assume that welded joint to be a fixed support. I hope my point is clear to you. So in this entire world, there are multiple type of supports. You can support a body through many ways, but all these supports can be divided into these three categories based on the type of behavior. What behavior is that? How that support is restricting the body. We can put them into either this category or this category or this category. Okay. If the rotation is allowed but the translation is restricted, we will put it in hinge support, this category. If the rotation is also allowed and translation in one direction is allowed, then we'll put it in this category. And if no motion is allowed, if it is completely restricted, then we'll put it in this category. Okay. So whenever you will see a diagram in the question, you will find any one of these supports. But in reality, it is not necessary that the supports will look like this. They can look like anything, but we'll assume them to be one of these categories. Okay. Now let's solve one or two examples based on free body diagram in order to check whether you have understood the concept or not. So let's consider this problem. A rigid massless member ACED is supported by a hinge at C and a rope passing over a frictionless pulley at A and D. The correct free body diagram of the member is. Understand what is happening here. We have a rigid massless member. I told you, right, in most of the problems, the weight of the member is considered to be negligible. Why? Because the forces acting on the member are so high that even if you don't consider the weight of the member, it is not going to make any difference. Okay. So the forces acting on this member are very high in magnitude. So the weight of this body is negligible compared to them. So in order to simplify the problem, we neglect the weight. Okay. Let's say the weight of this member is only 100 Newton and the force acting on this body is 500 kilonewton. So imagine 500 kilonewton and only 100 Newton. So this 100 Newton is nothing. Even if you ignore this, the reaction forces are not going to change a lot, right? Chalo. So understand. We have this member ACED. It is a T-shaped member. It is right now supported by a hinge support at C. And there are two ropes. One is connected here, another one is connected here, and these ropes are passing through this pulley. Okay. Now we need to draw the free body diagram. How the free body diagram will look? A, B, C or D. Now before you get into drawing the free body diagram, understand this first. This rope is a special type of support. This rope can only be subjected to tension. It cannot be subjected to compression. Can you compress a rope? If I give you a rope, can you apply a compressive force to the rope? No. The rope can be only subjected to tension, right? Now, how do you show the tension? Tension means it is pulling something. That is a tensile force, right? If I am pulling something, that is a tensile force. Okay. So now imagine how the free body diagram of the body will look. Whether it will look like A or B or C or D. Understand about the reactions. if I isolate this body from the hinge support at point C, I will get a reaction in X and a reaction in Y. So this will not be the free body diagram. This will not be the free body diagram. It can be this or this. Both are correct. Okay. But what about this and this point? These 2 points are connected to the rope. Now I told you that the rope can be subjected to only tension. It cannot be subjected to compression. And tension means you are pulling a body. So at point D, if I isolate this rope from the body, I will get a pulling force, not pushing force. The force cannot be acting like this. This will be a compressive force, na? So it has to be a pulling force. The tension will be something like this. Here also at point A, it is right now supported by this rope. So if I isolate the rope from the body, I must get a pulling force. The rope can only pull the body, it cannot push the body. So at point A and D, there must be a tensile force like this. So in this diagram, we have a pushing force. This is a compressive force. It cannot be true. So only this answer is possible, D, right? I hope this is clear to you. So although we can assume any direction of reaction at the hinge, I can assume the reaction in X direction to be right side or left side. I can assume the reaction at hinge to be like this or like this. I can imagine this force to be like this or like this. But when I consider the force acting due to this rope, it must be tensile, because it is 100% clear that the rope cannot apply a compressive force. So I have to apply only tensile force. Here I can't use my imagination. Okay, here I can't use my imagination. So here I have to apply a tensile force only. I hope this point is clear. Let's move on to the next question then. The massless rigid spanner shown is used to rotate a shaft. This is the shaft and this is a spanner. A pin fits in a hole at A. Can you see this pin? Can you see this very small pin? It is fitted at A. While a flat frictionless surface rests against the shaft at B. So at point A, the spanner is fitted into the shaft using a pin, and at point B, the spanner is resting on a flat frictionless surface. The correct free body diagram of the spanner is, the spanner is subjected to a force like this, and the mass of the spanner, the weight of the spanner is neglected. So what will be the free body diagram? A, B, C or D? Use your concepts. Just now we have seen about the pin support and the frictionless surface support. Frictionless surface means category 1, pin support means category 2. So at point A, we have a pin support. At point B, we have a frictionless surface. So how the reactions will be acting on the spanner? A, B, C or D? Let's find out. At point A, here we have a pin. So here we will get a reaction in X and a reaction in Y. So this cannot be true. This cannot be true. This can be true. This can be true. So A and B are eliminated. Now C and D. At point B, we have a frictionless surface, and you can see that it's a very small surface but a vertical surface, right? The surface is very small but it is vertical. So the reaction must be acting normal to the surface, right? It's a frictionless surface. It's a very small vertical surface. So the reaction must be acting horizontal. It must be normal to the surface. So at this point B, we will have a reaction force acting in X direction. So this cannot be true. Only this can be true. So I hope that this question is also clear to you. Now, if you are wondering how I am going to solve the problem, how I am going to draw the free body diagram, don't worry. When we will start solving problems of statics, in every problem, we will draw the free body diagram first. Nah? So even if you are not able to draw the free body diagram right now, after solving a few problems, you will learn it. So don't take a lot of pressure. I have seen students taking a lot of pressure just in the first chapter itself. Don't do that. Even if you are not able to solve these two problems correctly, don't worry. Some students learn in the first problem itself. Some students learn after 2-3 problems. Some students learn after 6-7 problems. Some students learn after first chapter. But eventually everyone learns. The most important thing is you have to be persistent. You have to be persevere. You have to try again and again. So when we will start solving problems of statics from tomorrow, we will draw all these free body diagrams. After a few problems, you will get habit of this and you will start solving the problem. You will start drawing the correct free body diagrams. Okay. So for today, this is all. From tomorrow, we will start solving the numericals of statics. Thank you so much for attending. I will see you guys tomorrow at the same time, 7 p.m. Till then, bye-bye. Take care. Good night.